for a function to be surjective. So one-to-one informally is nothing in the codomain is hit twice. Yeah? Everything in the codomain is hit at least once. That's what it means to be surjective. So all of this is what it means to be one-to-one. A function is called onto if and I'll leave out the at least once. Just if it's hit at least once. It can't be hit half the time. And so let's parse that out into something formal. So, what's another way of saying everything in the codomain? Yeah.
For all x1 and 1k. That's the domain of it?
Yeah, except, yeah, codomain. For, and I'll use y instead of x just because it's an output. Outputs are usually y values. It doesn't matter what you call the variable. B is the codomain. It is hit. What does it mean for y to be hit by the function? Yeah.
Like there exists x in A such that f equals to y.
Oh. Well, that's what it should mean. To be hit by a function means that some input goes to you. How do people feel about backwards default exists? People comfortable enough as long as it's at least just on the board? Alright. So let's write that down. A function is called onto or surjective if for all y in the codomain there exists at least one x in the domain such that f of x equals y. And if you want to show something is onto, this even tells you what you need to prove. You need to prove that statement, so you should start by considering anything in the codomain. You then need to come up with some input which solves that equation. And well, you have lots of practice solving some equations, but that's enough practice to know that there's no single unified technique, and sometimes it's hard. But you at least know what sort of statement you need. A function is called bijective or invulnerable if, what does it mean to say a function is bijective? Yeah. Yeah. If f is one-to-one and onto. And why are functions that are bijective called invulnerable? It's because they have inverses. Right? If you have a bijection, you can talk about the inverse to that function. And what do I mean by that? Given a function from A to B, another function going the opposite direction is the inverse to x. And we write b equals f inverse. If for everything in the domain, what should the inverse applied to f applied to A always be equal to? What should that be? Yeah.
A.
Awesome. For every b in the codomain, also known as the domain of G, f of g of b should be equal to that help? What should it be? Yeah. Cool. People feel okay? Yeah. Nice. And the big payoff in terms of, well, bijectivity is this proposition. If you have a function, then that function, it's a proposition, you shouldn't have to prove that, then f is bijective if and only if there is a function g satisfying the definition of the inverse of f. And if you want a proof of that, then what you want is the first extra credit / challenge problem in this class, in which you will get the correct super formal definition really of what a function is. Because did I actually define a function? I said it was like a rule that takes a thing in A and gives you a thing in B, but that's not a definition. That's too informal to be a definition. What's a rule? The correct definition appears in this challenge problem, and you will use that definition to understand what composition really means, and to prove bijectivity, if and only if invulnerability. Nice. How many people think they're going to take a look at that? Not like now, but maybe at some point in the coming month. All right. Groovy. All right, so now we're ready to actually get on to real analysis. And step one in doing real analysis is, what are the real numbers? And for us, the real numbers will be specified by 3 words. The real numbers are a field. There's what we'll do first. The set of real numbers is a field which happens to be ordered. And as an ordered field, the real numbers are complete. So that's what we'll hit last. And the first couple of these are, well, field is a word that, well, let's see, how many of you have already taken the abstract algebra class? All right, what's a field? Informally, if you like. What types of things can you do in fields? All right, so a field is a set of numbers, a set of things, where you can add, subtract, multiply, and divide. Now it sounds more familiar? Yeah, so a field, saying the real numbers are a field, is just saying that. So plus, minus, multiply, and divide. Walk. And we'll specify what that means in the following conditions. Now let's talk about order. Are the real numbers ordered? Can you say, like, this real number comes before that real number?
Yeah.
Yeah, what does that make you think of? What symbol? Yeah, that's all the order axioms are. The order axioms are making sense of that symbol. And completeness is not a word that you should have heard before. Somehow what the completeness of the real numbers is trying to get at is everywhere where you expect a real number to be, there is one. There are no gaps in the real numbers. But that's very vague, and it'll take us a while before we get to the notion of completeness. So for now, let's talk about fields. And let's start with the definition. A field is a set together with 2 binary operations, plus and multiply. And what do I mean by binary operations? I mean if you take 2 things in F. If you add them together, you're still in the field F. If you multiply them together, you're still in the field F. The real numbers, as you're thinking about them, intuitively satisfy that condition. There's an operation called addition, an operation called multiplication. If you add or multiply real numbers, you get real numbers. Awesome. So far, so good. I'm not trying to be precise, because I don't know what the real numbers are. I'm trying to make up a definition. These operations are associative. What does the associative law say?
If this one can make it to everything makes sense. The one where you can, like, slide it into parentheses and slide another one out.
That I think
Very
is
pictorially.
Yeah, I think you're talking about distributivity. Maybe I should write associativity. So associativity is the rule that says that you don't always need to write parentheses. It's the operation that says x plus y plus z makes sense, even though it's only binary. So associativity says that those two things are the same, so you didn't need to draw the parentheses anyway. Okay, that's what you meant by slide.
Yeah.
Okay. I interpreted the word slide incorrectly. I interpreted it as distributivity. And multiplication should distribute as well. X times y times z is the same as x times y times z. These operations are also commutative. What should commutative mean? Yeah, well, it should mean this, right? If you put two things in one order, you can put them in the other order and you get the same thing. So for all x, well, I guess I should have this. For all x and y in f, x plus y equals y plus x, and x times y equals y times x. The distributive law. What does the distributive law say? Yeah.
You could do sort of the Algebraic distribution.
Yeah.
The one that we did.
It says that if you see x times y plus z, you could rewrite that by multiplying x by each of the signs. There is an additive identity element called 0, which satisfies a condition. Those of you who have taken abstract algebra, what condition should the identity satisfy? Yeah. Yeah. For all x in f, x plus 0 equals x. Groovy. There is a multiplicative identity called 1, such that for all x in f, what should happen? Yeah.
X times 1 equals x.
Yeah, perfect. There is an additive inverse for every x in the field f. There is an additive inverse called minus x, which satisfies what condition? What does the additive inverse do? Yeah.
X plus the negative x equals 0.
Yeah. And right, I said I would, subtraction was supposed to be one of the symbols, and it wasn't in the list, but you see, that's what subtraction should mean. For every x which is not 0, there is a multiplicative inverse called x inverse, which satisfies that. Well, what should the multiplicative inverse do? Yeah.
Multiply to 0, so x times 0 equals 0.
Multiplicative inverse.
Inverse.
You should be able to undo multiplication. What can you tell me about x times the inverse to x? Yeah. Yeah, it should be 1. So those are all definition-y things. So none of these are things that are claiming are true. These are all just definitions. A field is a set together with some operations which satisfy these 7 or 8 conditions depending on whether or not you count 0. How do people feel? Does that make sense? So you'll notice a few things. Like you said that it better be that x times 0 equals 0. That's a thing that you know to be true. Do you see that anywhere in those axioms? All right, so if that's actually true for the real numbers, and we haven't written it in the list of axioms, that orange line had better follow from those 7 things. And that's what we'll do today. We'll start explaining, take any of the things that you know are true for the real numbers when you multiply things together and add them together, prove that those things are actually true. That's going to be the goal of today.
We're going to have to apply x times 0 to all 7 axioms, right?
We're going to have to apply x times 0 to all 7 axioms. How do you mean?
Like, we have to make sure, in order for that statement to be something that's proven, we would have to make sure that we have to illustrate that it could be performed in all kind of 7.
Ooh,
Sorry.
Here is the type of thing. So we get to assume all the field axioms.
Okay.
So we're not going to try to show that any particular thing is a field in this class. That's something that you might remember doing in...
That's something I think I remember doing that. Sure.
Yeah, absolutely. Because in abstract, you're interested in lots of different fields. We are interested in one field. This is the only field that we care about. So,
Like that. Okay.
and like none of those are hard. Like it's just lots of things to check. No one of them is actually difficult. So I get to assume all the field axioms, and then we will try to show x multiplied by 0 equals 0. So that's what we'll need to do at some point. Cool. So we have these axioms. Maybe it's worth saying explicitly. We now know what addition and multiplication mean. Subtraction means a plus minus b. Division means a times the inverse to b. The algebraic properties of the real number line are summarized by the following axiom. Axiom is in a thing that I will assume and will not try to prove. It will be part of the definition of what the real numbers are. The axiom is the real numbers are a field. So, let's study these field axioms, see what happens. There was one of the things that we want. We could go out of order, but I think I'm going to try to avoid going out of order. There's a flow that I want. So, in the list of axioms, you'll notice that there was this claim there exists an additive identity called 0. Could there be several additive identities? Conceivably, right? There's no law against it yet. But they're short that are not. Let's prove that there's only one additive identity. Let's prove uniqueness. So we get to assume that there exist things like identity elements 0 and 1. We don't get to assume that they're unique. There could be lots of different things that act like 0 or act like 1. Here's what we need to prove. Let f be a field. Let 0 hat be an element of f. Satisfy the condition that for all x in R, x plus 0 hat is equal to x. Then I claim that 0 hat is equal to 0. So absolutely anything that acts like 0 is the honest-to-God identity element of the field. Right? And that's something that seems that if that weren't true, we would want that added to the list of field axioms. Since we didn't have it in the list, and it's something that we sure think should be true, we need to prove it. Let's try to prove it. And similarly for 1. Let 0 hat, yeah.
I just wanted to clarify. So, it was possible you said this and I just didn't quite fully catch it. But why is it, if we want it to behave this way, why should we prove it instead of like just taking it as an axiom and then go running with it?
So here is an answer that comes to like the stuff you did in abstract algebra about checking field axioms. If you have a list of axioms that contains one extra thing, then if you want to prove something's a field, you need to prove one extra thing. So it's useful to have a list of axioms that is as short as possible and has no redundancies.
Okay.
It also lets you get to like what the actual things you need to be a field are. If there's redundancy in your list of axioms, then like one of them isn't really an axiom. It's something that you should prove.
Okay.
Cool. So let us prove. So there is the thing we want to prove. So let's start with the assumptions. Let's let 0 be in the field F. And let's let it satisfy the properties that give you the 0 element. And similarly, let's let 0 be the 0 element of the field. I need to show that those two things are equal. And so that there's not much content there, but it's useful to say, here are the things I know, here's the thing I want to prove. Let's try to prove it. And the procedure that this proof will follow will be by studying this expression, 0 plus 0 hat. So let's try to evaluate that two different ways. What should 0 plus 0 hat be equal to? Yeah.
0.
0, right? Because anything plus 0 hat is that anything. By this assumption, 0 plus 0 hat is equal to 0. But wait, on the other hand, 0 is the additive identity element. So what's 0 plus 0 hat? Yeah.
0 hat?
Yeah. Anything, 0 plus anything is that anything. So 0 plus 0 hat is 0 hat. Oh wait, does that mean 0 is equal to 0 hat?
Yes.
Yeah, they're both equal to the same something.
Excellent.
And this is a neat idea that is important in some algebraic proofs. If you want to prove that two things are equal, one way to prove that those two things are equal is by realizing those two somethings as some more complicated expression that you can simplify two different ways. So look at the other thing in this theorem. Proposition? Theorem. Let one hat satisfy the condition that defines the additive identity. Then one hat is equal to 1. Do you think that a similar proof might apply? Homework. Proof claim 2 of this theorem. That was supposed to be a borderline of 3. Think you could do it? Nice. There's some other existential lines. There was the stuff about inverses. Any element has an additive inverse which satisfies that f plus minus f is equal to 0. Should a single element be able to have lots of different additive inverses? I sure hope not, because otherwise, that means that negative 2 isn't actually well defined. Right? It could be like 5 different things. Let's prove that it's actually well defined. Theorem. Let's let G in the field, let's let F be a field, F be an F. Let's let G satisfy that F plus G equals 0. Then G is equal to negative F. And same thing with multiplicative inverses. Let's let F be not equal to 0. 0 doesn't have an inverse, so I thought I'd assume it's not 0 from here to talk about its inverse. Let's let G satisfy that F times G equals 1. Then G is equal to F inverse. Shall we prove? And let's try to prove it, and we'll do it. Maybe let's scratch mark off to the side. So I'll think about the following expression, minus F plus G. Associativity says that I don't really need parentheses, but let's guide it with parentheses anyway. What can you tell me about minus F plus G? What should that be equal to? Yeah.
0 plus G.
0 plus G, because minus F plus F is 0 plus G. All right. But what's 0 plus G? Yeah.
G.
Groovy. So G is equal to this expression. Let's evaluate it a different way. That should be the same thing as negative F plus F plus G. And let's ask the same question. What can you tell me about F plus G? Yeah. Yeah, it should also be 0. Maybe, let's see, that's not quite what I assumed. I assumed F plus G is 0. Yeah. Equals negative F plus 0. What's negative F plus 0? Hey, does that do it? Yeah, so let's just put the rest of the words in. Yes. So let's do the thing. So, start with the assumptions. Let's let F be a field, let F and G be an F. And, this is a mistake. Assume F plus G equals 0. You do need to give the assumptions. All right, so by exactly the logic we used, negative f plus g is 0 plus g by the axiom of the additive inverse. 0 plus g is g by the axiom of the additive identity. Similarly, negative f plus g, well, by associativity, I can move the parentheses around, and this is just exactly what we did off to the side. What's f plus g? Cool. And negative f plus 0, Gesundheit, is negative f. Gesundheit. Groovy. So now, you somehow know what I'm going to do next. I'm going to say this is equal to this is equal to this, so this is equal to this. And that's exactly what I want. Let's just write that sentence. So we see negative f is equal to negative f plus g is equal to g. And so negative f equals g, which completes the proof. How do people feel about that argument? Think you can probably do a similar thing to get the thing about multiplicative inverses? Yeah, I think so. All right, so now we're ready to get to the thing that is written there. Anything times 0 should always be 0. Let's prove that. Let's let a be an f, then a times 0 is equal to 0. And we'll do a similar trick. We'll evaluate a times 0 plus 1 minus a in two different ways. And maybe we'll even try to motivate that a little bit. Now let's do it off. No, there's enough space in the merger. A times 0 plus 1 minus a. And let's just evaluate that by doing whatever. We'll just evaluate that somehow, and then we'll evaluate it in a different way. How would you want to evaluate that expression? What's the first thing you would want to do? Yeah.
I want to simplify the 1 and 0.
You want to simplify the 1 and the 0 by saying 0 plus 1 is equal to 1. Nice. What next? Yeah.
I'd apply the multiplicative identity of a times 1 equals a.
Cool. And what's a minus a? 0. So I better be able to evaluate this in a different way in order to get a times 0. And so, yeah, let's try to evaluate this in another way. So what's another first step you could do to that initial expression? Yeah.
Distributive property.
You could use the distributive law. You could distribute the a onto the 0 to get a times 0 plus a times 1 minus a. All right. And what would you do next?
I would
You're good.
I would then multiply out the a times 0 and a times 1.
Cool. Well, a times 0, I don't know what that is yet. So
Yeah,
just
we'll
leave
just
that.
leave that as it is. So a times 1. And then I will simplify the a's, and we'll be left with a times 0.
Oh, neat. So a times 0 is equal to the thing at the top is equal to 0. There's a proof. In terms of time, I feel like I'm talking a little slow. Do people want to take the time to fill in the spaces in the actual argument? People would like to see that done? Let's do that. So, let's do it. Consider any a in the field f. You need to start with your assumptions. We will proceed by evaluating a times 0 plus 1 in two different ways. And I mean, some of our ways are determined by those initial steps, but yeah.
I don't mean to backpedal at all here, but I want to take a quick look at the second half of the work. I was curious, if we get a times 0, if that's what we're trying to prove, how does just having a times 0 prove that it's equal to 0?
equal to that, is 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 equal to 0.
Oh. Oh. Okay.
Yeah. Yeah.
How do you know where to start? It seems somewhat arbitrary. Like we have this.
Oh, sure.
Around circles and then rows the first line.
Yeah. So like there is like a clever false step. So let's talk about how you might get to that false step. Like guessing that this is a good thing to evaluate is something you kind of just need to screw around with a little bit. So let's try to screw around a little bit and like try to get to there. So I won't try to come up with a proof. So kind of start with that and see like, well, what's some stuff you can do to both sides? So I guess you could like subtract a from both sides. That would tell you something. No, it's add a to both sides. Okay, let's do that. So you can do the same thing to both sides. So what I want to do is like turn the left-hand side into something that I can like factor some stuff out of. So here's something that I could factor some stuff out of. Fair enough. I can turn that into like a times 1. And so like there still was like a weird false step there, right? But I mean not every proof just follows right from definitions. Some of them need a couple false step. And the whole point of making that move was trying to figure out how to backtalk. And well, what is that equivalent to? I can subtract the A over to the other side, and then I get exactly that false line. So that's like a way to get at something. So try to look for something that has to do with the thing that you want to understand, but is somehow complicated looking and can be simplified in 2 different ways. I think there's like the philosophy. Try to look for something that has multiple simplifications. And maybe if you simplify in different ways, you get different looking things. Nice. Because that really is the core idea here. You need, like, there was a sneaky false step. And now, well, in the time that I may have stalled right there, some of you may have already filled in these lines. Right? What was step 1? By the distributive law, how could you rewrite this expression? Yeah.
A times 0 plus A times 1 minus A.
Yeah. And what is the next thing that we did in the thing off to the side where we distributed cost? Or what would you just want to do now? Yeah.
Additive identity tab? No, multiplicative identity.
Yes. By the axiom of the multiplicative identity, you can get that. What next? Yeah.
Apply the definition of subtraction, I guess. I think for the additive inverse.
Yeah. Yeah, so what can you tell me about A minus A? Cool. What can you tell me about A times 0 plus 0? What's anything plus 0?
Just the thing for the A times 0.
A times 0. And the thing that gets used there is the behavior of the additive identity. Yeah, that gets us down to A times 0. Good. All right. And similarly, you would evaluate using the other set of instructions. If you're forced to use the axiom of the additive identity, that thing is 1. A times 1 minus A
by the axiom of multiplicative identity. A times 1 is A, and A minus A is equal to 0 by the axiom of additive inverse. So since both of these expressions, this expression it was equal to both A times 0 and 0, we conclude that the two things are the same. A times 0 is equal to 0. Neato. People feel okay?
So is the last line just blank then? Oh, I meant like right up there. I think that was all.
Oh, yeah. It looks like I gave myself an extra space.
Okay.
Groovy. So I think I have enough time to do one more thing. Is 1 equal to 0? Better not be.
I imagine it's something we should prove.
Yeah, probably.
Okay.
So it better not be. But in fact, the list of axioms that we had just for field allows for one silly thing. Let's think about the field that contains only 0. And let's just see if these properties hold. So let's take the thing called 0. If I add and multiply zeros together, do I get zeros out? Does associativity work if everything is 0? Does commutativity work if everything is 0? Does distributivity work if everything is 0? Yeah. Does this work if everything is 0? Yeah, there's nothing. 0 is the only thing, so everything is equal to everything. That too? Is there an additive inverse to 0? Yeah, it's minus 0, which is 0. And let's drop down here. So let's suppose that f contains only 0. So does it then follow that for absolutely, well, does it follow that for, here, multiplicative identity. So let's suppose that everything is 0. So if this thing is supposed to have a multiplicative identity, that multiplicative identity better be 0. If x is already equal to 0, then is x times 0 equal to x? Yeah, 0 times 0 is 0. So the multiplicative identity rule works if the only thing in your field is 0. And if everything is 0, then nothing needs to have an inverse anyway. So the last axiom is just vacuous. So, in fact, the set containing only 0 is a field. It's like a stupid field, but all of the axioms are satisfied. So, yeah. Yeah. Let's write some sentences maybe on the board. We're taking f to be the field that contains only 0. And let's write down that seventh axiom. For all x in f, if x is not equal to 0, then some stuff happens. So let's talk and think about if-thens. So an if-then statement with a false hypothesis is automatically true. Right? It's definitely true that if I am a purple unicorn, then I'm green. Right? That's a true statement. There are no purple unicorns, so every purple unicorn is green. Same thing here. There's no element of this field that's non-zero. So absolutely everything is true about every non-zero element of this field. That's what I meant by vacuous. There's nothing to check. So here is the claim. If f is a field in which the additive and multiplicative identities are the same, that is, a field in which 1 equals 0, then that field is the 0 field. So adding the assumption that 1 is not equal to 0 is the same as saying this field contains at least 2 elements. It's not just 0. Oh, Christ, I'm at time. Neat. So I should stop. So maybe as you pack up, I'll give the idea of how this proof will go. So if 1 is equal to 0, then you would want to consider any element of the field and get that element to be 0. That's going to be the goal of the proof. Take any element of the field, show that that element is equal to 0. And maybe we'll talk through it while people kind of pack. If you have any field element, what's that field element times 1 equal to?
The field element.
The field element. But 1 is equal to 0. So f is the same as f times 1 is the same as f times 0. But what is f times 0 equal to? 0. So what is f equal to? 0. So every element of the field is 0. That is the proof.
Okay. I think.
That was a very fast. Go fast.
Have a good one.
See you.
I have a quick question on associative homework.